da, 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 da. Today we are going to talk about residual odds because of that gosh darn glare. I wonder if I can turn off my lights and open my window. Watch this. Yeah, there we go. Except now I look like Two-Face from Batman. Arrgh. So we're going to talk about residual plots now. And when you look at residual plots, what you want to see is just random scatter of dots, like this. We've got no patterns, we've got no shapes, no animals, just a bunch of dots. That's the right thing to see. Now, if you see a pattern, that indicates a problem. And the problem, wait, I'm doing the wrong side, huh? Which side of my face should I squint? Got it. These are the 5 assumptions: linear, constant variance, normality, random residuals. Now, depending on what book you look at, sometimes they'll only list these 3 because these 3 are things that you cannot control. They're natural forms of the data you find, but there are statistical ways to deal with it. We're not going to learn them in this class. This one, if you didn't gather the data independent and randomly, that's your problem. Go get random data. And residuals average 0, the computer will do that automatically. But let's talk about what you would see in the residual plots if these were not true. For linear, you're going to be seeing something like this. See how this is not just random scatter? It's following a line. It's following this pattern here. You'll see curves. You'll see bends. There's flowing to the data like it's going somewhere. That should not be happening. If it's happening, that means your data was not linear to start with. Here it was below the regression line, and then above the regression line, and then came back to the... Now let's talk about constant variance. Constant variance, you'll see a pattern like this. See how it's a triangle shape, or a wedge, or an arrow? There's small variability here, and that variability is increasing, increasing, increasing until you've got lots of variability here. That's non-constant variance. If you see this, you know you've got a problem with that second assumption. If you see this, then we have an indication that the variance is not normal. Because look at what the histogram would be. Tons here, and then less here. The histogram would look like a lot of residuals there, and then tailing off to fewer residuals there. What do you see in this plot? We're seeing outlier here, outlier there, right? These outliers, or it's more dense on one side. That's an indication what you have is non-normal regression. Now keep in mind, for all 3 of these, those aren't your fault. That's the nature of the data. There are ways to deal with it. You need to take a more advanced regression class to talk about it. This one says you didn't gather the data randomly. So imagine you went to someone's house and you asked the dad how much he eats pork. And then you asked the child how much they eat pork. Well, this is non-random data because you're going to get answers from everyone in this family that's similar because either they all had it for dinner or they didn't. So what you're going to see in your residual plot is going to be a clump of data. Here's that family and the other family. This is your fault for getting the data the wrong way. There are statistical ways to actually deal with this, but this clumping or related groups is the sort of thing you watch for to know that the independence assumption might be violated. Now this last one says the residuals average 0. So on all these graphs, 0 should be right in the middle because the residual says how far were you from the regression line, and the regression line should be right in the middle. What would it look like if it wasn't? If you look at this plot, here's the line for 0. If that was our balancing beam, would this tip? The answer is yes, it tipped this way because there's more data up here than down there. And so it's not balanced at 0. What this means is you have this data and the regression line didn't go through the middle of the data. It kind of skimmed along the edge. How does that happen? Well, if you're using a computer on your data, it won't happen. And it doesn't happen unless someone else did a regression line and you used their regression line on your data. And sometimes people discover to their surprise that doesn't work. For example, on the West Coast, they discovered the relationship between how many chirps a cricket does and the temperature. And when they took that to the East Coast, they had this kind of problem. Because the West Coast crickets are somehow different than East Coast crickets. You need a different regression line. Please keep in mind, real-life scenarios will often have more than one problem at the same time. For example, what do you see here? You can see that there is a wedge shape, but also a curve. It's curving while it has a fan. So we have a problem with linearity and a problem with constant variance. Now, it's a common question for students to say, I can look at the original plot of the data and tell that. For this example, the original day would probably look like, and now you can easily see how these problems occur. When you're young, your salary is low because you don't make a lot when you're 11, and it jumps up pretty steep until you get into college where you stop making any money at all, and then after college, your salary levels out as you go into your career. But it fans out because there's lots of choices you could make about your career. So there's linearity and non-constant variance, and it makes sense. Why are we hammering on the residual plot so heavily? It's because for more advanced regression, 12-dimensional regression, which you can't draw a picture for, it's still two-dimensional residual plots. So this is a tool worth learning. So this is a non